So that is how you would access data. But how do you determine if this data that you wanted is in the cache or not? Huh? Or if the data is in the cache, how do we find that data? So what do we have? The information that we have is address of data, and we also know how the cache is organized. How the cache is organized? Let us say I say that the cache is organized in terms of a direct map cache. What does direct map cache means? Direct map cache means that depending on the address of my data, I would write to only one particular location in the memory. What does that mean? Let us say direct map cache pe aate hain, but there will be only one location where I will be able to write inside the memory. That is what is called as direct map cache. Then there are set associative caches where you say that okay, इस cluster में कहीं पे भी लिख सकते हो आप. Okay, and so on. So in a memory, in a cache memory, there is something, as we said, which is called as tag. After that tag, you actually have the address bus is broken into different components like index, block, and byte. So the byte will tell you which word, which byte to pick up. Block will tell you which block. Okay? Which amongst the which word in a given block. So for example, if your block is 16 words, so which of these 16 words in the block do you need to access? Then index, by row, and then tag. What do they all mean physically? Let us look at that also. We say that there is a 24-bit address for a 16 kilobyte cache. Just calculate for 16 kilobyte, how many address bits do you need?
14.
Huh?
14.
14, sir.
You need 14 address bits. है ना? 16 kilobyte, you need only 14 address bits. So what to do of the additional 10 bits?
And they represent this tag index.
Yes, they become tag. Okay. Now, in a memory, suppose your data is organized such that there are 8 bytes of data in every row. So how many in every block? So how many address bits would you require to identify which byte to be sent to the processor?
11.
3.
11.
3. I have a word.
3.
Now I need only 3 address bits to identify which of these bytes to send to the processor. If I say that there are 8 bytes per word or per line, how many blocks or how many lines can there be? Total capacity is 16 kilobytes. I said 8 bytes per line. How many lines can be there?
So 12K lines.
2K lines.
2K lines, sorry, 2K lines.
Now, if you had to decipher 2K lines, how many address bits would you need?
11.
11. Do you see 24-bit address bus got split as 10 bits for tag, 11 bits for block selection, 3 bits for byte selection in a given block. So in the memory, what were you storing? You were storing 8 bytes of data, 10 bits of tag, and 1 bit which could be valid bit. We'll talk about the purpose of valid bit a little later. When you access a particular line or a location, the tag is fetched along with it because it is in the same word. When the tag is fetched along with it, you compare the 10 address bits of the incoming data and whatever was stored over here inside the memory. If they match, you say this is the data corresponding to that 24-bit address. If they do not match, you say I have a miss. Are you able to see this? Is the purpose of tag clearer now? Raghav, you had a confusion regarding purpose of tag. Is the purpose of tag clear now?
So actually, I'm still processing. Actually, the bit splitting is just about it.
So your main memory was huge. You would access it with 24-bit addresses. Your cache is much smaller. You need only 14 address bits to access the cache.
Yes, sir.
But the system, when it sends out the address, it sends out the address regarding the main memory. So it always sends out 24-bit address. And you have to ensure that the address that you fetch from the cache is matching the total 24-bit address. That it matches the lower 14 bits is evident because you see that in the physical memory there.
Yes, in the
14 bits is clear.
Yes.
Now we need to ensure that 24-bit is matching. So 14 आपने check कर लिया. Remaining 10 bits, you actually store whatever the address was alongside the data in the memory itself. So that when you read the cache, you also read the address from where the top 10 bits from where the address was fetched initially. Now you compare the top 10 bits of your address sent by the processor with the top 10 bits stored over here. If they match, there is a hit. If they don't, there is a miss.
So basically, tag is only that sort of MSBs of that address, total 24-bit address kind of thing only.
Yes.
Yeah.
That is one way to understand it.
Yes, sir. Thank you, sir.
Okay. Is it clear for everyone? Any questions?
Sir, I have one question.
Yes.
Can we go to the previous slide where we have definitions? Yeah. Sir, over here, there is a separate field for the block as well as a separate field for the tag. Sir, why is it required, sir? Because tag is something which is unique and a tag is associated for a complete block, right, sir?
So this is referred to this bus is the 24-bit address bus.
Yes, sir.
This block is 11 bits. Byte is 3 bits. We did not have any index in the given example in the next slide. 10 bits.
Okay.
Is it okay?
Sir, but in the case of suppose if we go for set as associative cache, then we'll have index as well as the block.
Yes.
So
yes.
at that point in time, then block and tag will having both of them would be redundant, no, sir.
No, we will just see that. We will just see that.
Yes,
ठीक है?
Yes, sir.
So उसमें क्या होगा? अभी आपने 11 bits block के लिए दे दिया क्योंकि set तो था ही नहीं. As soon as set comes, let us say this is 4 bits as associative. 9 would go to block, 2 would go to set.
Yes, sir.
But you will still need the 10-bit tag.
Okay.
You will still need the 10-bit tag because your memory is 14-bit addressable. If you use a larger cache, if you instead of 16 kilobyte, you would use 32 kilobyte, your memory becomes 15-bit addressable.
Yes.
Then you will need a 9-bit tag.
Okay.
You use a still larger cache, 64 kilobyte. You need an 8-bit tag. Because it is the number of address bits which you are not able to use while accessing the physical memory there.
Sir,
Yes.
sir, you said that when we go for set associative, I mean, first of all, just to clarify, the block bits are referring to the line number, right?
Line.
So, but in set associative, we don't know in which line our data would be. We only know in which set it would be, but the line could be anything. So how can there be bits for a line number?
So we will see. अभी देखते हैं.
Like, am I right in set associative? We only know in which set the data would go, and then we match the tag in every line of that set. But we don't know in which line the data is.
Yeah, we will see. We will just see. Don't worry. Set associative को कैसे एक्सेस करना है अभी देखते हैं. पहले डायरेक्ट वाला समझ में आ गया.
Yes, sir.
So let's not run ahead of the class because there are some students who will not understand that also. This part until here it is clear, everyone?
Sir, मतलब like different blocks जो एक tag होगा that will be referring to multiple blocks. I mean multiple blocks can have the same tag.
Yes.
So sir, basically we are doing this tag and all this thing just to maintain because we have the 24 that system bus is similar same.
Is it just, or is it something like I want to go home and I do not want to end up in my office location? I'm wanting to access that 24-bit address. I want to access only that one, not another random 24-bit address.
Okay, so sir, like we are breaking the whole address into parts. When we are calling some bits, we are calling for the data, some for the block, some for the tag, and such
Yes.
so on. Okay.
The entire address has to be matched.